Hello everyone, are you able to hear me?
Yes, sir. Yeah.
Okay. So we'll just wait for some three more minutes and see if anyone else is joining. If not, we'll start the session. Okay, so there is a clash with some other session, is it? Okay, what session is that?
Sir, it is regarding the projects.
Okay.
Projects introduced to the four subjects regarding that session from Andrew, sir.
Oh, okay. Okay. Oh, yeah, then it is understood, right? So otherwise, generally, how many of uh, how many join this session generally? Any idea, like rough estimate? Okay. So what do we do now? Okay, we just continue. I don't see the point of stopping now.
Hello, sir.
Yeah.
Sir, before you start the session, I would like to say something about our GPA, sir.
Okay.
Sir, the problem is, first problem is I am getting confused where to, in which programs should we add those dummy features, and in which programs we shouldn't, and and also in the in week 4, uh, probably GPA 2. The Sometimes what happens, the statement of the question is not clear.
Okay, okay.
So if you can help me out with this problem, it would be really helpful, sir.
Okay, we'll see, right? So we'll see. I am like really not sure what to do if many of them don't join. But I'll just go ahead because since you 10 of you, 10, 12 of you have joined. So I'll just go ahead with what I have planned and then we'll get back to this at the end.
Okay, sir. Okay.
Okay, so how many of you here have watched the lectures for week 5? Okay, so I gather that most of you haven't watched. Okay, so anyway, what I'll do is I'll just it'll be more of a lecture kind of a session. Okay, so this will be more of an introduction or even a detailed discussion on week 5. I'll assume that you don't know anything about what is being covered in week 5. I'll only assume that you know content till week 4. Okay, so you can this will be more like an open session and you can stop me in case you have any questions. Is that fine?
Yes, sir. Okay.
Okay, so this will be more of a lecture. We'll start with the course outline. So we are into week 5 of the course, right? So you have already seen linear regression, polynomial regression, least square classification. You have studied perceptrons. That is these three bullets you have already seen. Okay, what you are yet to see or what you are going to see for the rest of the 8 weeks are some more classification algorithms. In fact, most of the other weeks will primarily be about classification. So week 5 we learn this technique called logistic regression. That is this week. Next week we'll learn something called naive bayes. Okay, so and in week 7 we learn something called softmax regression, which is an extension of logistic regression, which we'll study today. Okay, so that is week 7. This is another important algorithm or technique called SVMs, which we'll do in week 8. Week 9 will be what is known as decision tree, and then week 10 will be about something called an ensemble technique. How do you combine uh, multiple models, right, to do classification or regression? And week 11 will be about clustering. If you remember, clustering is different from either classification or regression, right? It's a different kind of it's like an unsupervised setup. And finally, we'll end the course with something called artificial neural networks. Okay, so that's roughly the course outline. So we are somewhere here, right? So the bulk of the content we are yet to see. Okay, so that's a brief outline. So as I said, please stop me when you have any questions. Otherwise, I'll just keep going on. So the story so far has been what we have studied linear regression. We have also studied polynomial regression in weeks 2 and 3. And then we started looking at classification. So what are the two models that we have seen so far? Anyone? What are the two classifiers that we have studied so far?
Sir, least square classifier, least square classifier, and
Okay, least square classifier, and that is correct.
perceptron, sir.
Okay, that's correct. Okay, so we have seen least square classification and we have seen perceptron, right? So that is where we are now. Okay, so this is another question. So what is one similarity among all these 4 models that we have seen? We have studied 4 models, right? Be it regression or classification. In all, we have seen 4 models. So can you tell me what is common among all these 4 models? Something very peculiar which stands out. Does anyone have any idea? Any guesses? Okay, we calculate loss is one answer. Okay, we calculate loss, but that is I won't call that a striking similarity, right? So I mean, you also have data for all the four models, right? You also use training data to train four models, but that is not something which is, very. I won't call it a striking similarity. Any other answers? Just think for a while. There's one. There's something which repeatedly turns up in all four models. No one else wants to go.
Sir,
Yeah.
sir, can you please tell what is the one striking similarity?
Okay. So I was waiting for someone to talk, right? See, otherwise it becomes very difficult, right? See, I don't know whether someone is there or not. So I can just go on talking, but it'll be boring for you also and as well as for me, right? So I expect someone. So rather than typing it in chat, right, you can unmute and tell me what you feel. It can be totally wrong. So I don't mind if, in fact, I'm happy if you give the wrong answer, right? Any answer. So some answer I want so that we can move forward.
Okay, sir.
Okay. So any answers? Any other answers?
Maximizing the loss function.
Okay, that is okay. We do that. So we calculate the loss. We try to optimize the loss function. But these are all things that we do in all ML models, right? So just just think about what happens in each. So I'll just go back to each. So you have 4 models. So what is the equation that you write for each of them? What equation do you write for linear regression? So what is the governing equation?
XW minus Y transpose into
prediction minus expected value
Okay.
loss.
Okay. So if I want to predict, if I want a prediction on a data point X, so how do I do that for linear regression?
We apply weights on the features.
Okay, you apply weights on the features. Can you tell me in terms of one equation, how will it be? Like
XW minus Y, like XW will predict.
okay, XW will predict, right? So can I say it is W transpose X? Is that fair enough for a single data point?
Yeah, that's fine.
Okay. So for
But
polynomial, yeah.
W transpose is this I can't understand. Like if I have let's say I have a feature matrix of 5,4 and W then should be by that should be 1 W should be 4,1, correct, sir?
Yeah.
Now if I do W transpose X, then it will become 1,4
No.
into
So when I say W transpose X, I'm looking at one data point, one feature vector. X is a feature vector and W is a weight.
Okay.
So in that sense, it is W transpose X, right? So for polynomial regression, also it is W transpose X, but X is you add a lot of other features also. Now, what is the is there something similar that you do for least square classification? So what do you do in least square classification?
We are getting the labels as 1 or 0.
Correct. How do you, so if a new data point comes to you, how do you predict that label? Whether it is 1 or 0, how do you know that?
Sign function.
Okay, sign function is applied on what?
On XW.
Okay, again W transpose X, right? For a single feature vector, I apply it on W transpose X.
Yeah.
Okay, now what about perceptron?
Perceptron is only binary. Same like.
Correct, it is very similar. So what, again, you apply this sign function on what?
XW only.
Sorry, on what?
XW.
Yeah, XW, again for a single feature vector, it is W transpose X. Okay,
Yeah.
so now can you tell me what is common among all these 4 models?
multiplying with weight vectors.
Correct, right? So see, the basic idea is linearity. So this is very important. So we are essentially doing this W transpose X in all 4 models, right? Of course, it is XW, but XW is what? XW is nothing but W transpose X done for each data point. If there are M data points, if you do W transpose X for each of these M data points, that is XW, right? So it is important for you to know both XW and W transpose X, right? Don't forget, this is in some sense more fundamental. It is from this that you go and get XW.
Sir, can you please that can you give the relation between XW and W transpose X? I actually confused with that.
Yeah. So see, the way it is so you have see, let's say X is some feature vector, right? 1, 2, 3, 4, right? So 4-dimensional vector, and your weights are how many weights will you have?
5.
Okay, assume that this is the dummy feature, right? So I already have the dummy feature, so I'll just assume that I have, say, five weights. Okay, so always I write them as column vectors. So this is, let me write it as a column vector itself so that we don't get confused later on. This is 1, 2, 3, 4, right? So 1, 2, 3, 4. Okay, so W can be anything, but let me just 1.1, 2.3, 1.5, and say 2. Okay, so this is X and W. Now this is one data point or one feature vector X and one weight vector, right? So there's only one weight vector always if you're doing binary classification or simple regression. So if I want to compute this, I do this, right? I do W transpose X. W transpose is 1 cross 4, X is 4 cross 1. Okay, now assume that you have not just one X, but you have many X values. So this is X1. Let's just do 3 values of X, right? So 3 data points you have. You have X1, X2, and X3. Okay, so X2 is, let's say, 0, -1, 0, and then X3 is, say, -1, 2, 1, 4. Okay, so we have 3 data points. Now if you are doing, say, something like regression, right? What will you do? You will do y1 minus W transpose X1 whole square. So this is the loss, right? So sum of squared errors. So I would do this for all these points, right? So I'll do y2 minus W transpose X whole square plus y3. Okay, so is this part clear? I hope everyone knows what this is, right? Okay, so now this is like a vector form, right? I'm writing the prediction. So prediction is what? The model prediction is h of x equal to W transpose X. This is the vector form. Okay, now how do I express this in the matrix form? I do it this way, right? Always remember this convention will follow throughout the course. The rows of the data matrix, or this is called the feature matrix or data matrix. So this is called the feature matrix or the data matrix. You can call it either way because it has all the data points in your data set. So in the feature matrix or the data matrix, the rows will be the features, right? Meaning each row will correspond to one feature vector. Okay, so this is very important to know. And this convention will stick to this convention throughout the course. So let me just so how many rows will this X have for this example?
3 rows.
Yeah, it should have 3 rows, right? So let me just write it down. 1, 2, 3, 4, 0, 2, 0, -1, -1, 2, 1, 4. Okay, so this is X. Now assume that the labels are given by y1 equal to we need, let's stick with the regression in this case. So y1 is 1.2, y2 is say 4.5, y3 is say 10. Okay, so x, okay, w. So now what will w be? W will just be this one, right? W doesn't change. It's just as it is. So now if you want to write xw, it is nothing but this matrix times this particular weight vector. Okay, so this, can you see that this is the same as w transpose x or x transpose w? See, this is x1 transpose w, x2 transpose w, and x3 transpose w. So do you get this part? No?
Yeah.
Okay, so this is what, so this is something you must all be comfortable with. So I'll just complete this. So this is nothing but x1 transpose w, x2 transpose w, and x3 transpose w. Okay, so and if you want to write the loss in terms of the matrix form, how will you write it? This L will be xw minus y. That will be this vector, right? So what will xw minus y be? Xw minus y will be, and just make sure that this is completely elaborated so that there are no other. So this will be minus y1 minus y2 and minus y3, right? So can you now tell me what the loss will be in terms of matrices in this matrix form?
xw minus y transpose into xw minus y.
Yes, that is correct, right? So that is correct. Okay, that's, these two expressions are the same. Okay, one uses the data matrix or the feature matrix, the other one uses the feature vectors instead of the matrix. So you must know both. Okay, right? So I hope you're all know at least
that is x transpose w, right? How come w transpose x is same as that?
because they are, this is dot product, right? X transpose w and w transpose x is the same, right?
Okay.
Sir,
Yeah.
sir, why all of a sudden instead of using the vector formulas what you have written just now, we started using for each data?
Sorry, can you come again?
Yes, sir. Actually, before these classification videos, whatever formulas we were dealing with, those formulas were written in the form of vector only. Like we were not dealing with individual data like now we are doing. So why all of a sudden we started we started with formulas which deals with each individual data?
Okay, that's a good question because we need to know that also, right? So see, both are important. You need to know what happens to one feature vector at a time, and you also need to know what happens when you do them, when you do that processing as a bulk data set, right? So in fact, you should go from the simple vector to the matrix case, right? So this, okay, we started doing directly things like xw minus y, but ideally what we should do is we should first start with this, right? Because it's easier to understand what happens to a single vector, and then you go to the matrix, right? You see that the matrix is, it comes naturally, right? Each row of the matrix is just one vector, one data point. So see, this is one request to you all, that do not memorize these formulas. These see, xw minus y is a very convenient formula, but you must, even if you forget xw minus y, you must always be able to derive it from scratch, right? You must know what xw stands for, right? Otherwise, there's no point knowing just xw minus y. Okay, so learn to see all these algorithms or techniques from both the vector perspective and matrix perspective. So that will always help. Okay, is this clear now that all four models that we have seen so far have used W transpose X or XW, whichever you are comfortable with?
Yes, sir.
Okay, so this is linearity. So the basic idea is that if you, this is what it means to be linear, right? So the linear regression, the linear comes from this, right? It's a linear relationship between the output and the weights, right? So W transpose X is this, right? It's the dot product, or X transpose W, both are the same. So now, can someone tell me what Wi represents?
Wait for ith feature.
Correct. It's the weight for the ith feature. But practically, right, from an understanding point of view, what do you think it means?
How much role a feature plays in?
Yeah, that's very good. Yeah, right.
Sir, Wi is weight for ith feature or ith feature vector?
Ith feature. That is a scalar, right? The xi is a scalar here.
Okay, sir.
Okay, so
But-
that is, yeah.
Sir, we use, I mean, in lecture videos, there was notation like Wi, but that I was written on top, like it is a subscript in your slide, but in the lecture videos, it was used as a superscript.
Yeah. So this is something that you must try and get used to, right? So here I'm using x1 to xn as features, right? Scalar features. Okay. So yeah, you are right. In the lectures, what we do is x superscript I will denote the ith training example, right? Or ith data point or ith feature vector. But here x subscript I, right? It denotes the ith feature. So there are n features.
Okay.
Yeah, so this is again very important when we do linear regression and all that. You must never forget that the weight has a very practical meaning. It is the importance of the feature xi. Okay, so if w1, let's say, is 10 and w10 is 0, right? What it means is that w1 is very important. The feature x1 is very important for me to predict my weight, whereas w10 is not so important. So that after you have trained your model and all that, you need to know what the features actually stand for. Okay, so that is linearity. Yeah, so this is just a repeat of what I told. You have seen this in linear regression, in polynomial regression, least square classification, perceptron. And finally, you'll also be seeing this in week 5, logistic regression. Interesting thing is you'll also be seeing this in week 7. You'll also be seeing this in week 8. So this W transpose X will never leave you. It will be there with you throughout the course. That's why I'm stressing so much on understanding what it means. Okay.
Thank you, sir. You explained very well, sir. Thank you.
Yeah, thank you. So now the setting is binary classification. Okay, 0 and 1. And we will look at something called the discriminative model, right? So logistic regression is an example of a discriminative model. Okay, so I'll come to that. I'll tell you what discriminative models are. But before that, let's look at what task we have to solve, right? We are given a feature matrix X. Okay, so typically it's M cross N matrix. So what is M? What is N? Do you have any idea what is M and what is N?
N is the number of examples and M is the number of features.
Okay, right. So we will be slightly, so the convention we'll follow is, I mean, very close to that. We'll say that the rows are the feature. You have as many data points as the rows, and each row will correspond to one feature vector, right? So there are n features. Okay, so this is the convention that we'll be following. If you remember, this is what we did, right? There were 3 examples and therefore m equal to 3. So in this case, this is a 3 by 4 matrix, right? So 3 training examples or data points and then 4 features. Okay, so that is what we'll be following. So the label vector is y. How many labels will be there in this? What will be the size of this vector?
So m by 1.
Correct. It is m by 1. And what will be the value taken by each component of this vector?
Label vector?
Yeah, label vector.
Actual value of the
Yeah.
label?
Yeah, what will be the values of the labels? I mean, what are the possible values the label can take?
Discrete values, sir.
Correct, discrete value, and assume that we are dealing with binary classification. So now, 1 and
0.
Yeah, so it will be 0 or 1, right? So this is the setting. Okay, this is what we have. This is given to us. Now what we have to do is we have to learn some function h. Okay, so finally, right, when you say I have trained an ML model, what does it mean? You have learned some function, you call it h, such that if you plug x into the function, it will give you the label, predicted label, right? It won't give you the true label. You don't, because you don't know what necessarily the true label is. You are making a prediction. Okay, so this is our task. Okay, this is what we want to do with our model. So I hope the task is now clear to all of you. Oh, okay, so I said that there are 2 types of models, right? One is called the discriminative model and another is called a generative model. So in this course, we'll be learning about both types of models, but we'll spend more time on these models called as discriminative models. Okay, so what happens in a discriminative model is that we try to learn or we try to model the probability of the label given the feature vector. Does that make sense? It's like a new concept, so may not be clear at first go.
So whatever the label is, we will try to predict that, right?
Yeah, so our final goal is to predict the label y. So what we are saying is that in the case of discriminative models, we will try to model this, the probability of seeing a particular label given the feature vector, right? So think about it this way. So I don't worry about how the feature vector is given to me, right? How it comes or from where it comes. This is a conditional probability, right? So you are given that x. Now your task is to tell me whether it is 1 or 0, whether it is cat or dog, or whether it is spam or non-spam or things like that, right? So you need to put it into 2 baskets. That is all you are worried about. You are not worried about from where your data comes and all that. Given this data point, given x, tell me where it falls. Is it label 1 or label 0? That is discriminative model. Okay, on the other hand, we have something called a generative model. So there I'm also worried about the data. So I'll try to model the whole data, right? So this is what is called a joint probability. So if you remember stats 2, this is what P of x comma y, right? You are trying to model the entire data set in some sense. Okay, so you are also worried about x, right? How it looks like. How do the data points actually look like? You are trying to model that also. Whereas that's a generative model. Whereas discriminative model, what you do is you are given x. Now you are trying to find out, okay, what label does it have? Okay, so we'll see this example and only then it will become clear. So logistic regression is a type of discriminative model, which means it's going to, if you plug in a value x, it's going to give you a probability in return. I'll repeat this. If you plug in a feature vector into the logistic regression model, it's going to give you one probability, right? What is that probability? How likely it is that this label of this data point X is 1. That is the probability that it is going to give you. All right. So this is where the assumption comes in. We make this assumption that the probability of seeing of getting a label of 1 given X is equal to the sigma of W transpose X. Okay, so now how many of you are lost? Does any of this make sense, or is it too confusing?
So, sir,
Sir, what is sigma here? Sir, what is sigma here?
Okay, right. So we'll go now step by step and understand this. The sigma is what is called a sigmoid function, right? So it's the mathematically it is what it means: 1 by 1 plus e power minus z. This is what it means. So the graph of this function is this. So here g of z, it's sigma of z basically. So just stare at this function for a while. Can you see what it is doing? Just forget about what all that came before you. Just look at this function. This is the graph of this function. Can you tell me what is special about this function?
Sir, is the area under this curve will sum up to 1, sir?
Okay. So you're asking, or you feel that it will sum up to 1?
Sir, I am asking. I feel that it will sum up to 1. I mean, it should sum up to 1. But I am also asking that is it summing up to 1 or not?
Okay, that's a good point. I will get back to you on that point later, right? But why do you think it should sum up to 1? I mean, what prompted you to say that?
Sir, I think we are plotting the CDF here. So CDF of probability should always sum up to 1. That's why.
Okay. Okay.
Actually, sir, GZ is representing the probability for different value of Z.
Okay. Okay.
If Z is less than 0, 50% values will lie, or GZ will lie below it, and 50% of GZ lie above Z0.
All right. Okay. So these are good observations, right? So you are right. We are trying to model a probability, right? So the first observation which is important is that this sigma of z lies between 0 and 1, right? So it takes some value z and kind of compresses that between 0 and 1, which is what we want, right? We are looking for a probability. We want a probability in some sense. And how do we get it? We use the sigmoid function, and as input we take W transpose X. Okay, for now, if you understand this much, that is good enough, right? Now, can someone tell me why this? So what is good about this particular model?
We are using probability.
Okay, that's one point. We are using probability. So I'm not saying that, okay, given a data point, this is always going to be label 1 or it's always going to be label 0. That comes later. So I'm just giving you a probability. I mean, if you give me a point, I'm going to tell you, okay, with 70% chance, this is going to be label 1. Okay, so the first good thing about this logistic regression model is that it outputs a probability. Okay, what else? What other good things are there about this model? So anything else apart from the probabilistic part?
So we know the value of X.
Sorry, can you come again?
We know that X has happened, like the event has happened. So it is taking advantage of that.
Okay, it is taking advantage of the fact that you already have X and then your only task is to get hold of the label. Okay.
Yeah.
Anything else? Okay, so see, the other important point is again this whole linearity comes in here, right? So we are again making use of a linear, in some sense, it's a linear thing, right? W transpose X. Okay, remember that what we have been saying so far, all the four models that we saw, right? Linear regression, perceptron, least square classification, all of them use W transpose X. And what are we doing here? We are again using W transpose X. Only thing is that we are outputting a probability instead of any real number. We are outputting as some number between 0 and 1, which we can interpret as a probability. Okay, so that is one big advantage of this model. Okay, so you have to know till this part. Now I'll now switch to a different set of slides. Okay, so yeah. So now after having seen what this model is, or at least the basics of this model, can you tell me what the answer to this question is? What is the output of a logistic regression classifier for an input X? X is input, it goes into the model. What comes out as output?
Discrete values are 1 or 0.
Okay. But even before you get discrete values of 1 or 0, what does it give you?
Probability of y equal to 1.
Correct. Probability of y equal to 1. Is that all or something else?
Given the value, given that particular feature.
Correct. Correct. You are right. Right. So this is very important, right? We must say the whole thing. So logistic regression model, if you treat it like a black box, right, or something, you don't know what happens. So a black box is basically something where you don't know what happens inside. Okay, all that you know is you only know input output. Input I know is X, output is P of y equal to 1 given X. So please remember this. This is very important. A logistic regression model accepts a feature vector as input and it outputs a probability. What probability is that? Probability of seeing a label 1 given the data point X. Okay, that's the model.
Won't y also be an input to it? Like, how does it know like what it has to predict?
That is its job, right? So that's the whole point of learning. So we learn the W in such a way that, so if you notice this, we learn these W's in such a way that when you input X, the model will know what to predict. So the learning part we are yet to come, right? So we are still in the model, understanding what the model is part. That is the part we are still.
Since it is a supervised learning, so we have to supply y also as input.
During learning, right? So we have not yet come to the learning part. So I have not given you what the learning algorithm is.
Okay, got it.
Right. So this is the model, is more of the inference stage, right? Prediction. At prediction time, what happens? You give X, you get a probability. Right? Okay. So few more terms. These are again terms you will be seeing throughout the course. You can treat this logistic regression as a two-step process, right? There is what is called a linear combination, right? Which is nothing but you just do W transpose X. So you linearly combine the features and the weights, that is linear combination. And you apply some kind of non-linearity, right? And this is called a nonlinear activation function. Don't worry too much if you don't get this at this stage. This is actually relevant for week 12 of the course. So in week 12, you will see why this makes sense. But this is some kind of a process that is very, very common in ML. You take a linear combination and then you apply some nonlinear function. Okay, so this is what is happening under the hood, right? Within the logistic regression model. Okay, right?
So is it the same as polynomial transformation?
Yeah. So see, okay, it is not, I won't call it same as polynomial transformation, because there what you're doing is you are adding more features, right? So you are adding more features and finally you still take the linear combination only. So for example, in polynomial, let's say you are given as input these features, right? You are given 3 features. What you do is, the next step in polynomial transformation would be what you do. x1, x2, x3, and probably x1 square,
Combinations.
right? So this is what this is like. Assume that I stop with this, and then you go ahead and do a linear combination of these features,
Okay.
right? So that is the difference. So here,
Okay.
yeah. Okay, so this is the model under the hood, as we call it. Now we come to the learning problem. Okay, all this is fine, but how do we learn the weights? Okay, so we have to learn the weights. Now, how do I learn the correct weight? So this is what we have to do now. Okay, so how do we do this? Okay, forget about this term now. It will become clear later. But just focus on this part here.
Sir,
Yeah.
y can be 0 also here, na, since this is level.
Yeah, y can be 0 also. It can be either 1 or 0.
Okay.
Right? It can be either 1 or 0, but the way I specify the model is by saying probability of seeing a label 1 given x. Okay, so yeah, now learning the weights. See, how many of you remember maximum likelihood estimate from stats 2?
The product of all the probabilities.
Right,
Yes.
right.
Yes.
Okay, right. So very briefly, we'll go over that. Okay, so see, if you have m data points, right? We have m training examples. Now, what we are saying is that this is the p of y equal to 1 given x, right? This is the conditional probability of seeing a label 1 given x. Okay. Now, you want to find out for what weight vector w will the possibility of seeing this particular data be maximized. So you want to find those values of that value of weight vector for which seeing this particular data set, the probability of seeing this data set will be maximized. Okay, so we call that the likelihood. So is that clear what we are doing here? What expression we have written here? Is that clear?
Yeah.
Okay, so since we have m data points, the probability of seeing, say, data point I will be p of y equal to yi given xi. Okay, so this will be the probability of seeing the ith data point, and since these points are independent and identically distributed, right? So they are all, you assume this is a very important assumption. If you remember from stats 2, you would have studied that this is what is called the IID assumption, right? So in this case, what you do is you multiply. You can easily multiply all these probabilities together. Okay, so now we'll resume the previous set of slides, right? So remember this, we are trying to maximize the likelihood of observing this data set given this particular model of the conditional probability. That's what our task is. Okay, so if p of y equal to 1 given x is this, what is p of y equal to 0 given x?
1 minus.
Correct.
Yeah,
Right, so
sigma.
it is just 1 minus this, right? So I hope this is clear to all of you. Now we'll come back to the expression. Okay, for there are m data points and you are multiplying all these probabilities. So I'm writing it this way. Now is this step clear to all of you, what I'm doing here? Do you see how I have gone from step 1 to step 2?
Looks like a binomial distribution.
Okay. Okay, tell me what will happen if yi equal to 1.
Second term will be 1 raised to 0. So it will be 1.
Okay, right. So the second term will just become 1. So sigma, so if yi equal to 1, this will be just sigma of w transpose xi, correct?
Yes.
So that is just p of y equal to 1 given x, right? So that is what we want. If yi equal to 0, then the first term will become 1, and this will just be p of y equal to 0 given xi. Okay, so in a single expression, depending on the value of yi, this will be either p of y equal to 1 given x, or it will be p of y equal to 0 given x. We have just replaced this by this kind of complex looking expression. So does everyone get this?
Yes.
Sir,
Yeah.
y can be 0 or 1. So this is or here. Na? So you should, I think, add these two probabilities. Why you multiply these two probabilities?
No, right? So see, y is 0 or 1, but yi will be either 1, like yi will be 1 or 0, right? I mean, it can't take both these values at a time. It will either be 1 or 0, and depending on what it is, my probability will be either p or 1 minus p.
Okay, sir. But when there is or, so then we add these two probabilities, sir.
No, right? So I'm not. So I'm not trying to. So in that case, then I could also argue that p plus 1 minus p is equal to 1, right? So probability will always be 1. So that is not the angle from which I'm coming, right? So I just want to express what the probability of y equal to yi given xi is.
Okay, sir.
So see, I'll maybe what we are trying to do is we are trying to given xi. Okay, so this is okay. So what I'm saying is this is sigma of w transpose xi. When is the sigma of w transpose xi? When yi equal to 1.
1. Yes.
This is 1 minus this when yi equal to 0. So what I'm essentially doing is I want a single expression for sigma for this instead of this case wise listing, right? I just want to express this as yi, right? So this is sometimes it becomes a bit tough. Yeah. So when yi equal to 1, this is what I want, right? Sigma of w transpose xi. So this is correct. Now when yi equal to 0, what will happen? I need this term, right? So I need this term. So I just put it here, but make sure that I raise it to the power 1 minus yi. Okay, so now tell me if this is clear.
Yes, sir. Now this is clear.
Okay, right. So I just want to express this whole thing in a single equation, which is what I have done here. Okay, so this is the product of the probabilities of seeing yi given xi. Now, what I do is I take log of this, right? So this is again typical. You are dealing with probabilities, product of probabilities. So they can become very small very soon. So I take the log of this. Okay, log of whatever you see there. Now, what do you think will be the next step?
Split the expression.
We will get a summation, sir.
Summation, yeah. Correct,
right? So we'll get the summation of whatever you see there. So this is something power something. So this will come down. This again will come down, and you will have this expression. Okay, so this is the likelihood, right? So this is called the log likelihood. of the data set. Okay, so I hope it's clear till now. So what is our task? We have to maximize the log likelihood. Correct. So we want to see what W will give me this. For what W will this data set that I see have the maximum possibility. So I have to maximize the likelihood. This is the same as what?
Derivative should be equal to 0.
Okay. Is there any other way of expressing this optimization problem rather than maximization? Can I do something else?
Can do minimization.
Okay. You will minimize what?
Negative of LW.
Correct. Right. So this is the same as minimizing the negative log likelihood. Okay. So you will see this term, minimize the negative log likelihood. Okay, so that's what we are doing here. Okay, so I have just substituted the log L, right, or L of W. I have just put it down here and added a negative sign in the beginning. Okay, that's all I have done. So this whole thing that you see here, right, this will be your loss function for logistic regression. So till this, is it clear? We have now come so far as defining what the model is, and then we have derived the loss function for the model. Okay, so I'll just list down the steps. So if you remember, you have data. 1 second. Just need to open. Okay, right. So for typically, what are the steps we follow? We first have the data. The 5 steps in the ML pipeline. Can you tell me what the 5 steps are?
Processing.
Sorry, what is the next step?
Reprocessing.
Okay. Okay, that is right. But
model. The model.
Yeah, the model. Okay. What is step 3?
A loss function.
The loss function. What is step 4?
Optimization.
Optimization. What would be the last step?
Evaluation.
Exactly. Right. So this is what we want. Right. So we have already seen the data. We have specified the data as some feature matrix of size m cross n. Right. So that is something we have seen. Okay, x comma y, right? So y is the label vector of size m cross 1. Okay, so the model we have again seen. The model is the logistic regression model, which is h of x equal to sigma of, okay. See, this is not the actual model equation, but this will return a probability, right? So this will give you the, let me write it that way. P of y equal to 1 given x is the probability of seeing label 1 given the data point x. So that is our model. And then we came across this loss function, right? I'm not going to rewrite it here. So loss is in terms of the weights, right? In terms of the weight vector. So this is my loss, and I have to minimize this loss. Sorry.
Sir, I'm sorry, I just joined. So the sigma that you use is similar to the G that professor uses in the videos?
Yeah, that is the same thing. So
same thing, right, sir?
This is the sigma that I use.
Okay, yeah, yes, sir. Thank you, sir.
Yeah. Okay, so loss. We are minimizing the loss. So we are at this stage, right? So we are done with data model loss. Okay. Now, so if you look at the lectures, there are two terms to this loss, right? Sometimes we call it the negative log likelihood, which you saw. The reason for that is this, right? We have the likelihood. We are trying to take the log of the likelihood, and we are trying to maximize the likelihood, which is the same as minimizing the negative log likelihood, right? So one term for the loss is negative log likelihood. The other term for the loss is called cross entropy, right? I'll very briefly tell you, both are equivalent, right? Both are the same. They mean the same thing in this case. Very briefly, I'll tell you why it's called cross entropy. Okay, so I'm just isolating this part inside the sigma. Okay, so it is yi log something plus 1 minus yi log 1 minus something. Okay, so this is what? This is of this form. This is minus p times log q plus 1 minus p times log 1 minus q. Does everyone see this form?
Yes.
Okay, so q is this thing. So what is q here?
Q is the probability of prediction.
Yeah, so q is the probability of seeing label 1 given x, right? It is the predicted probability. Okay, q is in some sense the predicted probability, and p is you can think about it as the actual, in some sense, the actual probability, right? It's not probability, but it kind of can get confusing, but so at least for q, we can understand that it is the predicted probability. Okay, so this term is called cross entropy. So I'll just very quickly tell you what entropy means. Just give me 2 minutes. Okay, so entropy, the typical definition is that it's the measure of uncertainty of a random variable. Okay, so what does that mean? This is just a formula. Okay, so don't get too worried about why it is called this way, but I'll skip to something which is more familiar. Okay, so do you all remember what a Bernoulli random variable is?
Yes, sir.
Okay, right. So if I toss a coin, right, the probability of heads coming up is p, right, and the probability of tails is 1 minus p. Okay, so it's like 0 or 1 outcome. That is where we use a Bernoulli random variable. Okay, so the parameter of success for 1 is p, and the probability of failure is 1 minus p. Okay, I hope you all remember that.
Yes.
Okay, so now what do I mean by entropy is this. If I give you a biased coin, okay, so biased coin meaning, let's say the probability of heads or p or x equal to 1, right? Let's say that probability is 0.9. Then if I plug that p value of 0.9 into this equation for entropy, I get something here, right, around say 0.4. Okay, I get a low entropy. So what do I mean by this is that if your coin is very biased, then in some sense there is very little uncertainty about the coin. I'll repeat this. If your coin is biased, right? Biased means what? If you toss it, then you kind of know what's going to happen, right? If a coin is very biased, let's say the probability of heads is 0.9, then 90 times out of 100, you know that it's going to turn up, right? Heads is going to turn up. So there is very little information that a biased coin can give you, right? Or rather, I would put it this way, that there is very little uncertainty for a biased coin. So at either end of this spectrum, you see that the uncertainty is very low, and therefore the entropy is low. But if I give you a fair coin for which the probability of heads or tails is 0.5, look at the entropy. Entropy is very high because I don't know what's going to come up, right? It could be either heads, it could be tails. So the measure of uncertainty is what this entropy fellow captures. Okay, I hope you all got that intuition of what entropy means.
Yes, sir. Yes.
Okay, so that is entropy. Now, entropy is, the formula for entropy is the sigma p of x into log 1 by p of x, which is the same as p of x log minus log p of x, right? 1 log of 1 by p will be minus log p. So this is the formula. So I'll just derive this. I'll just show you what this formula means in the case of a biased coin. So h of x, the formula is sigma p of x. So there's a minus sign. Log p of x. Okay, so can someone tell me what this represents in terms of probabilities you would have studied, right? What is this h of x actually? Sigma p of x into something is what for a random variable or for a distribution? Sorry, I couldn't hear you properly.
Expectation.
Yeah, that is correct, right? So it's expectation. So it's expectation of what? Yeah, so this is expectation of log p of x, right? So entropy is in some sense the expectation, right? On an average, what value does this log p of x take? Okay, so for a coin, for a Bernoulli distribution, for a coin, this summation becomes what? X can be either 1 or 0. So when x is 1, p of x is p times log p, and when x is 0, p of x is 1 minus p, right? And this is 1 minus p. So that is how I get this expression for entropy for a Bernoulli random variable as minus p log p minus 1 minus p log 1 minus p. Okay, so if I compare this, this is the formula, right? Minus p log p minus 1 minus p log 1 minus p. And if you plot this, this is the curve you get. At either ends, since you already know what the outcome will be, more or less, the uncertainty is low, so entropy is low. For the middle part, right, where the uncertainty is high, entropy is high. Okay, so now if you remember, right, I told that there are two terms for the loss function. One is negative log likelihood, another is cross entropy. So this cross entropy wala comes from entropy. Okay, so if you look at the formula, instead of h of p, you have h of p comma q. So there are, you're not in some sense comparing two distributions. Okay, so there is p of x and there is also q of x, and so there is not just entropy, but there is a cross entropy. Okay, so this is now if you expand this, right? If you expand this, you will see that for two Bernoulli variables, random variables, this will take this form: minus p log q minus 1 minus p log 1 minus q. Okay, so don't worry if you don't understand too much. It's like just remember that this is in some sense very similar to the entropy formula for a single random variable, right? Minus p log p minus 1 minus p log 1 minus p. So instead of P, you are going to substitute Q wherever the log is there. Okay, did everyone follow till now?
Yes, sir.
Okay, right. Even if you understood 75%, it's okay, right? I just want you to understand from where this term cross entropy comes. Okay, now compare this. What you have on the RHS is the binary cross entropy, and that is what you have on the left. So this is why you call your loss function. Where is it? This is why you call your loss function negative log likelihood or cross entropy. Okay, so that is this part. So we have come till this. We have seen data, we have seen model, we have. So now optimization. See, optimization, I'm going to skip. Okay, so that's one big derivation. You can check the slides for the optimization. So what I'm going to do is I'm just going to tell you what the gradient will be after the optimization. Okay, so let me just write it down. The gradient after the optimization. Okay, so before we go there, can you tell me what is the gradient? We take the gradient of what with respect to what?
Loss function with respect to weight.
Correct, right? So we take the gradient of loss function with respect to the weight. Okay, so this is the gradient. So nabla. So this thing is called nabla. Nabla is the gradient of L with respect to W will be is this correct? Let me just I just need to verify if this is correct. Okay, this is for a vector. So I'll just stick to the vector convention. Or maybe this is fine. Okay. So yeah. Okay, so this is the gradient of the loss with respect to W for logistic regression model. Okay, so now what will be the update process? The weight at time step t plus 1 is going to be weight at time step t, and then what?
Plus alpha and
There is this, I think, minus
Okay, minus
alpha.
learning rate.
Okay, times what?
Derivative of loss function with respect to W.
Okay, that is what we have here, right? So that is what we have here.
Yes, yes.
So let me write it this way. Okay, so now if you remember the gradient in linear regression, do you see some similarities here? Does anyone remember what was the gradient for linear regression or least square classification?
There was no sigma actually there, and everything is.
Everything else is nearly the same, right? There was no sigma.
Yes.
It was xw minus y, right? So that's the kind of unity that you see among all these models. It's very easy to remember also. So for logistic regression, you have this extra sigma. Okay, so that is the gradient, and once you have the gradient, you know how to optimize the function. You do gradient descent. You start with, say, a vector of zeros. So I start with W 0 time step 0. I start with a vector of zeros, and then I keep updating my weights. Okay, so this is basically what we are doing. Okay, so okay, Right. So far, has everyone followed what has been happening?
Yes.
Okay. So now we come to the interesting part, which is the geometry of the decision boundary. So what do you understand by the statement geometry of the decision boundary?
So, where we separate the two classes.
Correct. Correct. Yeah. So how do we separate the two classes? See, if you remember, I said in one of the earlier slides that this is a kind of a discriminative model, right? So I'm essentially trying to discriminate between uh, class 0 and class 1. Okay, so my whole point is to learn a decision boundary that tries to separate the zeros from the ones. So what geometry will be, what will be the shape of the decision boundary? How will it look? Okay, so let me go back to least square classification. What was the shape of the decision boundary there?
Was a straight line.
Okay, it was a straight line, right? So in higher dimensional space, we call it hyperplane, but in two-dimensional space, it's a straight line, right? So now let's, okay, so in a logistic regression model, what is this decision boundary? Okay, so that is the question we want to answer, because finally we want to, given a data point X, I want to predict, right? I want to predict whether it's labeled 1 or 0. So how, first of all, I must know how I get this prediction, right? So this is how I do the prediction. So remember that logistic regression outputs a probability. So if the probability that the model outputs is greater than 0.5, then I say that my predicted label is 1. If not, I say that my predicted label is 0. Okay, is this clear? This is the inference. This is how I do prediction for a logistic regression model. If I get a data point X, I compute the output of the LR model. If that output is above 0.5, I say that the data point belongs to class 1. If not, I say that it belongs to class 0. Okay, is there any question here, or all of you clear about this step?
It's clear, sir. No question.
Okay, right. So this 0.5 value is called a threshold. Okay, it's called a threshold. Typically, it is chosen to be 0.5, but you could choose it to be any number between 0 and 1. Okay, so we are now proceeding. So y equal to 1 if this is greater than 0.5, 0 otherwise. So can someone tell me how I will? So I'm telling you this. From this, you can get the decision boundary. This is what I'm telling you. Now, can you try to see what that boundary looks like?
It will be straight line at 0.5, the dotted line that we see.
See, this is sigma of z, right? So this is more like, this is the value for W transpose X on the X-axis, on the Z-axis. So your graph will be slightly different, right? It will be in, say, some other space.
Yeah.
Okay, so, okay, I'll ask you this question. So if sigma of W transpose X is greater than 0.5, can you tell me which part of this graph I'm talking about? See, W transpose X is Z. I am giving you that also. Sigma of Z is greater than 0.5. So what part of the graph are we looking at?
Upper
The
half.
first quadrant.
Correct, right? We are looking at the first quadrant. Okay. So how do we define the first quadrant? In terms of Z, what is the first quadrant?
Greater than 0.
Okay, so Z is greater than 0, right? For first quadrant. Okay. So Z is what here?
WTX.
Okay, so W transpose X is greater than 0. Correct? So notice, concentrate on this part. I say that the model predicts 1 if sigma of this is greater than 0.5, which is the same as saying the model predicts 1 if W transpose X is greater than 0. Okay.
But in that case, it will also include the quadrant below it.
Sir, it will be a straight line then after 0.
After sorry, which would be a straight line?
I mean, the geometry of the decision boundary will be a stepwise function, and it'll be I mean, it'll be a step at 0.
Okay.
That's my assumption. I mean, I am thinking so.
Okay. All right. But you must remember that this is the data points are not in this graph, right? So this
Yeah.
graph is just Z versus sigma.
Yeah.
Okay. So if W transpose X is greater than 0, okay. So this I'll just copy this and go to this scratch screen. So what I'm saying is one if W transpose X is greater than 0, 0 if W transpose X is okay. So have you looked at this kind of a setup before? For any classification model that you have studied in week 4, did you come across this setup?
Perceptron.
Correct, right? So for perceptron, you came across this, right? Only thing is that we would have said this is -1. Okay, but it doesn't make much of a difference. So can you now tell me what the decision boundary is going to be?
So still there is a confusion, like originally we said sigma of Z should be like greater than 0.
0.5.
0.5. So it means like it will be the top right quadrant, right?
It will be the top right quadrant in this graph, right? So
yeah.
Top right quadrant in this graph means what? Z is greater than 0 and sigma of Z is greater than 0.5, correct?
Yes.
So
is required.
Right. So from this, I can conclude that Z is greater than 0.
But in that case, it will also take the bottom right quadrant.
In that case, no, right? See, it won't, right? I mean, see, if Z is greater than 0, then sigma of Z is, okay, I'll write it this way. Okay, I get your point. This is the statement I'm making. If Z is greater than 0, then, sorry, some random function came here. This is the claim this is my claim.
Okay.
Okay. So, see, Z greater than 0, I agree. So it divides first and fourth quadrant are both in Z greater than 0. But if Z greater than 0, I know that sigma of Z is greater than 0.5, right? I am only looking at this curve finally.
Okay. Okay.
Right. So this will happen only if Z is greater than 0. And if Z is greater than 0, this will happen. So it's like both are if and only if kind of relationship.
Got it.
Okay, so W transpose X greater than 0 is what? It's just the case of your perceptron where you have a linear decision boundary, right? So it's a hyperplane again, right? So the decision boundary is a line separating the two data points. Okay, so the moral of the story is after doing all this, a logistic regression model also learns a linear hyperplane, or rather a hyperplane which separates the two classes. Very important point to know. Did everyone get this part about the decision boundary of a LR model? Or did any of you not understand what this was all about?
So considering that all these are similar in both the models, how do we decide which one to take when we are doing a classification problem?
Okay, that's a good point. So what we'll do is typically we'll start with, so there's no one correct answer, right? So these are all models. So there's one very popular there's a very popular quote in the statistics literature. So the quote is this, right? All models are wrong, but some are useful. So what you do is you run through all possible models, say logistic regression, least square classification, and then some more that we'll study. whichever gives you the best accuracy on your validation set, you will pick that, right? So if you are just going by accuracy as an evaluation metric, you look at whichever model gives you, whichever model is most useful, you will pick that, right? Because ultimately all of them are wrong. So in some sense,
yeah, all our predictions, yes.
Yeah, all our predictions.
One doubt, general doubt I have is, so like here we assume like we can divide the model, right? Divide the classes to a line, right? But the classes are mixed.
Correct. Yeah, that's a good point. So we have assumed linear separability. I mean, I won't say we have assumed. So this will do a good job if the model, if the data is linearly separable. If it is not, right, what we'll do is we'll do what we did in polynomial regression. We'll just augment it by using polynomial features, and we'll do the same sigma of W transpose X.
In case of classification, polynomial will be like we will apply and or on the features, like when we create a new feature from existing features, we will do logical and just ping the gun. And how will we multiply the two features?
So features, right? We are not going to multiply the labels in some sense. We are only multiplying the features.
Yes.
So x1, x2. So if I have x1 and x2, I can always multiply, right? x1, x2, x2.
Got it. Sorry. Yeah.
Okay, so now we'll very quickly go through. So what it all means, in fact. So we have been looking at gradient descent for a very long time. Okay, 4 weeks now. So I just want you to get this flavor of what gradient descent actually does. Okay, so in the case of logistic regression, this is the gradient. So it's m-dimensional vector x transpose. Okay, so I think I've changed my convention a bit. Okay, never mind. So see, the shapes, don't worry about them too much, but the gradient expression is this, right? So what it's actually doing is, okay, so I'll just let you stare at this slide for a while, and do you see what this slide is actually representing? What does it mean? What have I written on the slides? Do you get any idea about that? Can someone tell me what the slide is actually talking about?
Basically, the loss, like summation of all the errors.
Good. Yeah. So that's a good point. So what is the error here?
Predicted value minus the expected value.
Correct, right? So on the left-hand side, on this side, we have the predicted label. Sorry, not the predicted label, but the predicted value, the probability basically. And on this side, we have the true label, right? 0 or 1. So this term, what you see here is actually an error. It's actually an error term. What is the error in prediction?
Right.
So there are, if you have n data points, then you have n errors, E1 to En. Now this X transpose will be what? Each column will actually be one feature vector. Each column will be one feature vector. So your gradient is actually what? A linear combination of the feature vector and the error corresponding to that feature vector. The error in prediction corresponding to that feature vector. Okay, so actually your gradient is something that's as simple as this and as meaningful as this. This big formula is there, right? It's actually what? It's a linear combination of your feature vector times the error in prediction current error in prediction corresponding to that feature vector.
Yes, sir.
Okay, so in fact, this is true for all the models that you have seen so far, maybe with the exception of perceptron. You can actually interpret your gradient this way for linear regression and least square classification also. Only thing is that the sigma will not be there. Okay, so remember this way of thinking about the gradient. It's actually quite useful. Okay, so if you isolate a single data point, then this is what is happening, right? So you are multiplying the data point with the error corresponding to that particular data point. Okay, so that is something you need to know. Okay, so this is some visualization I had for SGD. Maybe I'll take it up in our next session, but it's not so important. But this is one animation for how logistic regression is actually working, right? So this is, so you see what's happening, right? So you have red data points which belong to class 0, green data points which belong to class 1, and you start with some weight vector W, right? Initially it's like the weight vector is like 0 0 kind of thing, and then slowly as the epochs progress, the weight vector keeps changing its direction and magnitude and comes to separate these two data points, right? So as you see, the decision boundary is linear. In this case, it's a straight line. Okay, so this is stochastic gradient descent, basically, not the full batch gradient descent. This is one animation that I want you all to keep in mind what's really happening in the case of LR. Okay, so yeah, so the final part. See, this is a comparison between these three classification models. So if you look at least square classification, perceptron, and logistic regression, and you compare the gradients, notice the similarity between 1 and 3, right? So in fact, the gradient expression is almost the same, right? But there is one minor difference or rather major difference depending on how you see it. Can you tell me what that is? So if you look at 1 and 3, can you tell me what is the difference between the two? Anyone? Any idea?
No difference. I don't see any.
Sir, in logistic regression is actually difference. This is related to probability something, but in least square, I think this is not the case.
Correct. Yeah, that's a good point. Yeah. Can you elaborate? Can you think more along those lines? E is related to probabilities here, whereas here it is not related to probabilities. So what difference will that make?
This is EI is in case of logistic regression. EI is error of probability of error.
Correct. It is the difference between two probabilities, right? So in some sense, you can say it's y. See, y is either 0 or 1, and y predicted is a probability. So you're right. Now, what I'm asking you is one step after that. So how will it affect the two algorithms here? What effect will it have? Okay, so how big can the error get here and how big can the error get here?
In logistic, it can only go max up to 1, I think.
That is true, right? That is, so if you recall, this least square classification is not very robust to outliers or Okay, that is one thing. And if you've already classified something correctly, so okay, I'll ask this one more question. If you have already classified something correctly, right? Let's say x1 you have classified correctly. What do you think will be the error?
It will be 0.
Yeah, it will be very close to 0, right? Or it will be almost 0. Whereas here, look at this here. Will it be 0 here?
Yes.
Always.
So y predicted value, like if it is accurate, right, it will be 1 in case actual value is 1. It will be the same, right, in both the scenarios.
Okay.
So since it's a classification problem, it could be either 1 or 0. So then it could be same, right?
It could be same. That's correct. Okay, let me put it this way. Okay, let me just quickly draw one graph. Maybe that will explain what I'm talking about. Okay, so I just want some collection of points. Say some of them are blue. Okay. Okay, so let's just make them numerous. So I have these set of points which are class, let's say class 0, and then say class 1, right? So these are my 2 points. Now you don't want the same pattern. So okay, so now let's say I have learned one decision boundary in the case of least square classification. Okay, so now a new point is added. Oops. Okay, a new point is added. See, 1, 2, 3, 4, 5, 6, 7, around 7 points are there, right? So 7 points are there in for the red class, 7 points are there for the blue class. So you train a logistic regression, you train a least square classification model, and this is the decision boundary that you get. Okay, now if I were to restart this training or continue this training by adding one extra point here, okay, now what do you think this error will be here? Do you think this y predict will be close to 1, or you all get my question?
You're talking about error, or you are talking about the value of y predicted?
I am talking about the value of y predict. So, okay, so what is the value of y predict in the case of least square classification? For a single data point with w being the weight, what do you think will be the value of y predict?
W into X.
Yeah, so it's w transpose x, right? So
Yeah.
that is your model. That's how you model it, right? So for this point, which is so far away from the decision boundary, assume that this half plane is w transpose x greater than 0. This is less than 0. What do you think will be w transpose x?
It will be quite high because it's very far away from the decision boundary.
Correct, right? So that is what I am talking about when I say that this is not very, so least square classification is not very robust to either outliers or, points that are, this is in some sense an outlier, right? Of course, it is on the right side of the decision boundary, but still it's like not representative of the class. Okay, but on the other hand, think about a logistic regression model. What will be the Y predict for it?
It will be sigma of W transpose X.
Yeah, exactly, right? It will be sigma of W transpose X. And what do you think sigma of W transpose X is going to be? Assume that this is class 1.
It will be 1. I mean, in the sense, it will be closer to 1.
Exactly, right? It will be closer to 1. So in that sense, logistic regression is very robust to, I won't say very robust, but it's much more robust to outliers compared to least square classification.
Okay, yeah, now got the point.
Okay, so all this that's like kind of the end of the whatever I had to say. But this is a point that I want you all to keep in mind that.
Sir.
Yeah.
Sir, I can't understand how this is more robust. Can you explain? Here,
See,
sigma is multiplied.
Yeah, see, this W transpose X is what? W transpose X is, in some sense, measures the distance from the hyperplane, right?
Yes.
The farther you are, the more the W transpose X, right? So for this particular point, this W transpose X value will be quite high. Okay, so this W transpose X, which is the Z value, will be quite high. And if Z is very high, then in your where is that? Where's that graph? Yeah, so if Z is very high, your probability Y predict will be very close to 1, right? Close to 1.
Yes, sir. Yes.
So if Y is close to 1 and if true label is also 1, right, for this point. So this error Y predict minus Y will be nearly 0.
Yes. Yes.
Okay.
I'm not getting this point, sir. Like Y predicted will be the 1 always, right? 1 or 0. It will not be.
Yeah. So yeah, correct. You are right. So sorry, this naming, I kind of named them incorrectly. So what I should have called it is, I must have used some other name. So, okay, right. So I should have called this H of X. Is this better, no?
Yes.
I should have called it H of X. So H of X is the model's output, right? So in the case of, this is what? This is least square classification. This is the model's output. And in the case of logistic regression, this is the output. So sorry for this naming. Yeah, I agree. This is very confusing names. It should not be Y predict. Y predict is always 0 or 1. It's the predicted label. So forgive me for this. It should actually be H of X minus Y. Okay, think about it that way. Now do you get it? Why this is the case?
Sir, if sigma is multiplied, then how this is more robust? I am not getting this. In the difference between the logistic and the least square is that only sigma is multiplied here.
No, not multiplied, right? This is sigma of W transpose X. So you are computing the value of the sigmoid function at W transpose X.
Oh, yes, sir. Yes. Oh, sigma is like a function. This is a function. And yes, okay. Now got it. Yes.
Right. So,
sir, I'm not clear. Like HX is also by prediction, right? It will
yeah,
also
but
give
it's
us 1 or 0.
No, right? So H of X is, see, there are 2 steps, right? So there are 2 steps. One is, there is something which your model outputs. That is one step. And using the model's output, you make some inference. So your inference step is basically like this, right? So it's like Y predict, your predicted label is 1 if H of X is, so for least square classification, I'm writing this, is greater than 0, and 0 if H of X is less than or equal to 0. So I take H of X, and then using that, I get Y predict. So Y predict is in this step of the process, h of x is in the previous step of the process.
This is new to me because I always expect model will give the predicted output. But
you are right. No, you are right. Your confusion is valid. The naming is kind of off here in this slide. Okay, so there are a few other things about sigmoid function which will make sense in week 12 and not now. Yeah, so that's all I had basically for today. If you all don't have any other questions, we can wind off and probably close.
this was an awesome session, sir. Understood everything.
Really, sir, this was one wonderful session, sir. You clearly explained what is mathematics behind logistic regression, sir. Great session, sir.
Thank you. Thanks a lot.
So next session, sir, you will take our.
So Saturday, see, week 5 and 6 I'll be taking, and then I'll be back in week 8, and then week 11, 12. So, but Saturday session, I don't know. Saturday, are we going to have a normal session or it will be revision? I am not sure for week.
It is shown as revision in the calendar.
Yeah. Then it won't be. Then I won't be there, but we will continue in week 6 after the quiz. Quiz is on coming Sunday or?
Yeah, it's on coming Sunday.
4th, is it? 5th May. Sorry, 5th June.
June, yeah.
5th June, okay. So mostly what will happen is we'll club the solve with instructor of weeks 5 and 6 together. So if you have any questions regarding the code, you can please post it on discourse.
Sir, if possible, sir, if you take the revision session, sir, this will be very helpful for us, sir. Please, sir.
Okay.
Actually, sir, you explain the concepts very clearly by taking the step by steps. So this become more clear, sir.
Okay,
That
sure.
possible, sir, you take them.
Okay, I'll see if that, I can make it, right? So yeah, sure.
Will we have any sample papers before the quiz? Previous term we used to have that.
Sample paper, I think there is one mock. There will be one mock paper for quiz 1.
When it will be?
Yeah, we have to release it. Yeah, we'll try to release it tomorrow.
Okay.
If not, I hope you all know where to find last year's quiz papers.
No, I don't know. Sorry.
Oh, okay. So I mean, I am not supposed to tell it here, but please try to contact your peer group. They'll know where to. So
okay.
They have already released all that. So
it's up on Discourse. You can get it there.
Right. Yeah.
Okay.
Sir, I have another request from you. I mean, I managed to scrape through Python because of your live sessions. So the NumPy and Matplotlib were only introduced in those in that course. So if you could take another session, I mean, based on whoever wants to attend on NumPy and Matplotlib, a little further on from that introduction, it would be really helpful.
Yeah, sure. That we can plan. So I am not. Unfortunately, this week will be tough. So I think most of you will be studying for quiz also, right?
Yes.
So
yeah, it could be after the quiz probably.
Okay, what we'll do is week 6, maybe Tuesday-ish, we'll try to have one for NumPy and Matplotlib.
Yeah, sure, sir. That would be really helpful, actually.
Exactly. Yeah.
Sure. Yeah.
I'm also struggling there. Yeah.
Yeah, sure. We'll try to have one during the early part of next week.
Yeah, sure, sir. And it could be need-based. I mean, you could state that in that this particular session is for this, and whoever is interested could join.
Yeah, sure. We'll do that. We'll do that.
Thanks a lot, sir. Thank you.
Okay. I hope the numbers increase next session because I was expecting at least 20-25. But yeah, whoever was there, I think we all participated well. So we'll meet again next week.
So today there was another session on a project change actually. So it overlapped. So probably that's the reason there are less number of participants.
Right. Yeah, I heard that. So I think it was by Andrew sir. And
Yeah,
okay.
yes, sir.
So nobody will miss a chance to be in a meeting with them. So I kind of get it. But so today is like I totally understand. But next week, let's hope that more participants are there. Anyway, so thanks a lot for joining. We'll meet again soon.
Thank you, sir.